It's my pleasure to welcome Keith Berry and Erin Dei to our lecture series. Thank you both for coming. I'm going to introduce Keith first and then Erin. So Keith Berry is the Director of Architectural Systems Management at Arktura, a leader at the forefront of architectural design and fabrication in Los Angeles. Arktura is a multidisciplinary office that creates architectural solutions and products, including ceiling systems, wall systems, rain screens, furniture, feature lighting, and more. Keith received his bachelor's in architecture from Cal Poly San Luis Obispo in 2008, where he developed an interest in dynamic forms and a passion for fabrication. He pursued these passions while working at Ilan Dei Studio in Venice, California, where he started as an intern and moved his way up to a leadership role, working on the design and fabrication of many projects, including 4 stores for the eyewear company Oliver Peoples and lemonade restaurants. Keith's interest in motion and its role in creating dynamic form led him to the UCLA Super Studio under Greg Lynn, where he received his Master's of Architecture 2 in 2014. Thanks, Keith, for joining us. And Erin Dei is a robotics technician at William Kreysler and Associates in the Bay Area. The office specializes in fabricating custom composites for architecture, building contractors, engineers, artists, sculptors, as well as the entertainment industry. Born out of the high performance boat industry, the company was founded to bring marine grade materials and techniques to construction and to provide quality craftsmanship and state-of-the-art technology to help clients realize sophisticated and effective solutions. Before working at Kreysler and Associates, Erin was an intern for Greg Lynn and at Peter Tolkien Architecture in Los Angeles. Erin holds a BA in Fine Arts from Southern Oregon University and received their Master's of Architecture from UCLA. Thank you both. Keith, you can start sharing your screen whenever you're ready.
Okay. So thank you for that introduction. That was great. Just very briefly about me, I'm sort of a architect that's always been more interested in, move fast and make stuff than designing skyscrapers or, working on projects at a massive scale. So I've always gravitated towards, CNC fabrication and designing fixtures and things of that nature. Really working with tangible materials. And so working at Arktura, I'm going to kind of run you through what we do as a company that is really designed for manufacturing. Let's see. Sorry, 1 second. Okay, is that sharing okay?
Yep, looks good.
Okay, so at Arktura, we're really looking at making design happen. So we consider ourselves collaborators in fabrication and in the world of architecture. So we're a kind of a group of architects, engineers, designers, programmers, artists, and really diving into what does it mean to manufacture products in the architectural space, and how can we leverage technology, parametric software, and cutting edge manufacturing techniques to make the most interesting and elegant architectural products and systems that we can. This is sort of our company ethos. It's very general of fueling possibilities. So whatever you can dream up, we can make it happen. So here's a kind of selected works of some things that I worked on at my tenure at Arktura. So going from even some of our more conventional products all the way through to kind of one-off, one-of-a-kind ceiling systems. So this is on the top left. This is a 71 above restaurant in downtown LA at the top of the Citibank Tower. The image below that is the one of our Atmosphera systems. It's a ceiling baffle system in Chicago. The upper right image is what we call our Sakare facade. This is a UNLV in Las Vegas. And then down below is a completely custom ceiling system somewhere in Texas. That's a completely one-of-a-kind solution. So the way we approach designing and manufacturing is really as we think of ourselves as not just fabricators, but actually collaborators. So what we want to do is get involved with an architect, and even at the earliest stages of what they envision for a project, and bring it as close to a manufacturable product with our manufacturing knowledge and capabilities as soon as possible. So we're really trying to engage at this design concept stage and collaborate all the way through the creative process, through developing, what's happening in a job site, software we might need to write, and all the way through to manufacturing and installation, and being involved all the way through a process, and not just providing product at the tail end of a project. And so we kind of live by this model of collaboration. So we're the manufacturer. We're also the designer sometimes, depending on what kind of project we're working on, and really engaging with all of the stakeholders on a project so that we're bringing the maximum amount of manufacturing intelligence and design and automation to the table. And the way that we're doing that, we use this conceptually, our approach of the physical toolbox and the digital toolbox that we can call on. We use manufacturing automation of CNC and laser, robotics, and as well as software-based automation. So a lot of parametric software that architects are used to using, like Grasshopper, as well as a lot of custom software that we'll write for manufacturing automation. So as an example, this is like sort of a typical Grasshopper script that we would write. Some of you may be familiar with this, and a lot of you, this will be something new, but this is how we're able to tell 3D modeling software to make automated pieces and parts for some of the products that we make. And so I think the best way to understand our process is looking at sort of our two major ways that Arktura operates in. We have a kit of parts model, which we call our architectural systems. And then we have the fully custom, sky's the limit design studio, which we call our solution studio. And depending on which one of those paths we choose is sort of how we approach the project. So for example, in this kit of parts, what we're really trying to get to is something that's very adaptable. And by designing a kit of parts, we're able to apply it to many different spaces and keep costs down, and really help develop something that is flexible and can be applied to many different types of architecture, and allow for unique solutions without having to start from scratch at every time. So really designing flexibility using parametric software and smart design of parts. So here's, for example, there's this atmosphere ceiling here. It's a kind of a waveform, and you'll see some others here, but they all kind of rely on the same base components. And then the software that we've designed allows us to make unique versions of each. So for example, there's a simple single fin, some channels, and a few pieces of hardware that is really all that goes into a system like this, but you get a very elaborate outcomes by using algorithms and software that we've written to vary each component slightly, and then leveraging our digital manufacturing tools to fabricate each piece uniquely. So here you can see it's a very simple kit of parts here. It's a couple ribs and some fins that cross it and some very simple hardware to attach them together. And by keeping this system really simple and allowing the software to create the variation and allow us to customize things, we're able to make really dynamic, unique installations for each project that don't cost a lot, don't take a lot of time to design, and are very unique and designed to each project to be a bespoke solution. So again, more of this parametric software that allows us to design in 3D and actually kind of evaluate different designs and solutions, and then also manufacture and review physical mock-ups of each version that we fabricate. So for example, in plan view, if this is a very simple version of that atmosphere system with a very simple basic inputs, you can manipulate the forms to make them curve. Something, as a design choice. You can also accommodate pretty common, architectural challenges like avoiding a column or integrating lighting and systems into essentially the same system with very few additional inputs, and still leveraging the same manufacturing techniques. So for example, these are 3 different versions of the same system. So this is this was the Oregon Ballroom up in Oregon that we just completed. It's actually made with a PET felted plastic fin, what we call a soft sound. And each profile is unique, and the sum total of these make a topographical map. Here's another version that kind of snakes through this lobby and this hallway and also undulates across to make sort of a surface, and then a kind of a similar one that curves both in plan and also in section. And so with just that base system, we can create quite a large variety of different system types. So quite a lot of variation by leveraging a smart system and parametric software tools. So the other path and the other kind of defining category of projects that Arktura works in is what we call our solution studio. And these are really like what I would call our flagship projects. These are the ones that, are one of a kind, standout feature pieces in a space that are really meant to be the focal point of the project. So everything from facades to ceilings, walls, custom kind of art installation and lighting, even some kind of custom furnishings sometimes. So we run quite a broad range. So I'll run through a few right here. So this is what we refer to as our Sakare system. And it's sort of an undulating kind of almost like a static or a sound waveform of various stainless steel square tubing, brushed stainless tubing arranged along this interior screen of this lobby. So here's the existing atrium, is kind of from the 80s and not super exciting. And then client's rendering of our system in there for reference. And then kind of a snapshot of how we take a really complicated system and design it into sort of panelized units that allow us to pre-manufacture large subcomponents of the system and then design it to interlock and install much faster and more efficiently in field than if these were all like individual pieces that got shipped to a job site, for example. So leveraging tools like site scanning, so laser site scanning, actually going out and measuring the entire space using laser scanning tools and generating a 3D model from that we can then design the system to fit, essentially perfectly without having to go and do additional measurements and wait for collaboration between us and contractors and other stakeholders to get the right dimensions to design the product. Here's kind of a typical drawing showing different modules and how those are broken up so that when they do arrive at the job site, the contractor knows which pieces go where and how to locate them and how to identify them. So label, automated software that labels and lays out where each piece is going to go. I'll show you some better examples shortly. And then here's kind of the final product is, as you can see in the bottom right here, each individual tube is then mounted to a frame, which then gets mounted to the building. So by systemizing each piece and leveraging the software tools, we can make a very complex system like this relatively easy to manufacture and install. So this is probably on the extreme ends of thing. This is really just a sculpture. And this was something where this is sort of the extreme end of Arktura designing and manufacturing based on a very loose concept. So this was sort of the rendering. It's not really a whole lot of information there, but the idea is there. And so from there, we're actually making concept renderings, physical mock-ups, and 3D model mock-ups that we can then interface with our client, with the architect, with the owner, and everyone who kind of needs to see what this might actually look like. Drawings again to show placement and technique. This one is unique where not only did the Mobius strips need to be designed, but also the suspension system. And so we ended up designing and manufacturing our own hardware. So all of these ball and socket joints to make all these crazy angles and allow a little flexibility in where each one of these ribbons lands in space. So you can see here, actually machining our own hardware from scratch, from raw stainless steel bars to make joints and things for something that is otherwise probably unbuildable. So this way we can leverage digital manufacturing technology to facilitate otherwise unmakeable products. So this is going to be a series of 3 different projects, all based on this kind of cellular structure. So this is a Starbucks inside LAX International Terminal. You may have seen it. Essentially, this was a concept based on like latte art. And so taking that concept and figuring out how to make something that can actually be manufactured was a really interesting challenge. So how do you design each piece? How do you figure out how to join them together? How do you get something like this into LAX? And so leveraging, again, software-driven solutions to design each piece. Each piece is unique. And so each piece has to be individually labeled and manufactured. And so really trying to use what the software can create for us to automate that process. Because if we were trying to do this manually, it would be just nearly impossible and far too expensive. So for example, the drawings we're going to create for this product also are going to serve as a guide for how to assemble and install it for the contractor who's going to put this in. So each piece is labeled, a diagram of where to start, how to kind of join each cell to its neighbor, and where you're going to build that in as you go assembling it. And some behind the scenes of this project was some of our bending software and plugged into one of our machines, showing how to make all these individual bends in every unique part, and then fully mocking it up in our shop before it gets painted and disassembled and packaged to go to the job site. And this is what it looks like installed. And so another version of this is sort of an iteration on this is kind of down a couple of concourses from that is Pinkberry, and sort of basing off the same concept, but a little more of a rigidized version is this cellular canopy, but it's sort of constrained within this wrapper of this of the edge of the material. Again, really leveraging the 3D tools. Also, you can't really use like, you know, span tables to calculate the stress and strain on something like this. So using finite element analysis software to actually size and design each, not only the size of the cells, but the thickness of the materials, how far apart they can be spaced, where they need to be supported. All of that can be accomplished using software like this.
Keith, it'd be great to wrap up soon. Sorry.
Okay. And then some, let's see, we'll fast forward. So last version of this same kind of concept. This was a fairly recent one that's a kind of a lobby feature, but again, leveraging the same tools to make something that's a little more dynamic and kind of a more of a hanging sculpture than an actual kind of canopy, but kind of all based around the same thing. Okay, we can end there. I'll turn it over.
Great, thank you so much. Erin, if you're ready.
Hello. Okay, let me see if I can get my screen shared. I'm going to keep this fairly short and sweet since I am working under a pretty strict NDA. So unfortunately, I can't share any of the most fun things with you guys, but please, please, please ask me all the questions you can. In all seriousness, I just got authorized to use renders this past week, so that's the situation. And that took reaching out to the project architect and construction manager directly. Let me get this closed. Share screen. And view. Full screen mode. All right, so my name is Erin Dei. I'm a pretty recent UCLA graduate. I graduated 2 years ago from the 3-year program, and 2 weeks after graduation, stepped on with Kreysler and Associates. Just as a brief introduction to my company, we work with, or the company I work for, we work with architectural composites as well as commercial and artistic applications. Kind of as they mentioned in the introduction, the company originally started with like a foundation in nautical manufacturing. So we take that same high degree of quality and ethos to architectural fabrication. My role is technically now a digital fabrication engineer, but robotics technician isn't too far from it. I do everything from developing and continuously improving production strategies to setting up robotic programs. I'm going to discuss a little bit more later in the presentation. We're currently working on the Lucas Museum, but I'm going to introduce you to the company and the company process and composites in general, just before we start, just to kind of contextualize what I'm talking about, as it might be new to several people, to a lot of the students who are watching. One of our most notable projects before our current project that we're working on was the SF MoMA project. As you can see, the rippling patterns from Sonetta, we were actually able to make these molds using a CNC hot wire cutter. So basically using Grasshopper to program the hot wire cutter in specified paths. Kind of going into what composites are. Composites are something that you probably take for granted in your life. It's going to be carbon fiber or fiberglass resin. So anything from chairs you're sitting on to cars and other vehicles. How we do it at Kreysler is we start off in most applications milling foam. This is a picture from our Green Island facility. We have 2 facilities in the Bay Area. One is at Green Island and the other is at Mare Island, which is an old military base. I'm currently working in the Mare Island facility, but again, due to NDA, I can't show any pictures of our facility. So here you can see a very large CNC machine originally used for nautical applications that is milling the foam mold for one of our projects. We then go to prepping the mold and applying a mold relief, so we can then take our fiberboard or foam substrate and then apply a mold resist that will then allow us to take the fiberglass off. Basically what we do is we have the fiberglass that's then impregnated with a resin, and that is layered to create a rigid surface that is about 5 pounds per square feet. So it's for extremely lightweight applications. I would like to emphasize that while we do work in a highly digitally motivated process, for every 2 programmers, there's probably about 40 craftsmen working on the shop. This is Miguel impregnating the carbon fiber resin. I'd like to highlight him in particular because he's been with the company for almost 35 years now. And as a programmer and somebody interested in digital processes, I always like to walk the floor and look to people who are doing these processes by hand for inspiration in regards to how to approach complex problems. We can see here that the fiberglass is being embedded to hold onto a frame. This allows the, otherwise it would be a sort of floppy or semi-rigid facade to then give it structure and then allow it to hang on the building. This project for SF MoMA was given a finish using a sandblaster. Gives it nice, and which provides a nice uniform finish. Our current project is a little bit more complicated because we're doing a cut finish, and unfortunately I can't share any images of the finish or the process, but that's what has been occupying most of my time and providing most of the challenges in regards to robotic fabrication. Another thing I'd like to plug about Kreysler is basically the ingenuity in regards to all stages of production, including shipping. The SF MoMA facades were shipped in their own mold to site, where they were then hung in place. So to go a little bit into my own background, before starting at UCLA, I did work for Peter Tolkien and Greg Lynn, and I also did some research into digital fabrication with Julia, as well as working at the shop. Here's a few quick slides about the Sagrada Familia project. It's a project by Gaudi. Mark Berry, who is one of the programmers on site, was basically able to finish the 100-year project by using robotics in order to execute some of these more difficult doubly curved forms, and he had programmed several of the details that Gaudi was able to only sculpt by hand. Here's a few slides of some of the research there, where we were looking at case studies into the forms as well as the scripting used to generate them. This is a great example of a project that could only be accomplished by computer-aided design. And unfortunately, I don't have any slides here, but I would also like to emphasize teaching experience and working at the shop when it finally came to arriving at Kreysler and being able to take on complex problems with robotics and CNC machines. So again, I'd like to apologize for kind of lack of images and not having too much of a presentation put together just because I'm under a very tight NDA, but I would like to present what I think has been some of the more interesting projects that I've gotten to work on in my time post-graduation. This is the Lucas Museum of Narrative Arts. I'm working for Kreysler and Associates, and we're doing the facade of the building. The architect is Mad, and our client is the Lucas Museum of Narrative Art. We're also working with several subcontractors. So I'll introduce a couple renders. As you can see, there are nearly 1,500 unique facade panels, ranging anywhere from about 12 feet to a little over 40 feet. One of the challenges working on this project has simply been the sheer number of unique components that we have. With my role in particular, I am providing the finish as well as a lot of, as well as the surface cuts on the panels. We're working with extremely tight tolerances, and that's been one of the greatest challenges, is not only the unique facade panels, but also the tolerances, which are on average per panel about 1/16 of an inch for any of the cuts to the paddle bottoms, sides, or face. You can kind of see how the panelization strategy is working here. And we have about a 7/8 inch reveal on all of the facades. So getting these panels to fit tightly and precisely has put in a lot of burden on robotics in particular, as well as calculating things like shrinkage and warpage on the initial CNC manufacturing end. So I'll walk you through a couple of the aerial slides. So you can see a couple, this project is going to be in South LA. It's currently under construction and it has an anticipated opening date of 2022. So please go and see it when it's open. And a couple more renders. Yeah, again, it's extremely difficult for me to share images, but a lot of my day-to-day work does involve Rhino and Grasshopper, as Keith had mentioned, he uses pretty heavily before. One of my current challenges that I've been working on the past couple weeks is looking at robotic kinematics and optimization, and the challenge of pre-planning when we have so many different panels that we bring into production on a day-to-day basis. So basically, when we bring objects into the cell, we utilize tools that were not really made for architecture, such as industrial robotics, 3D scanners typically used for surveys, as well as PowerMill and other robotic programming other robotic control software that are really meant for more repetitive reduced in a production facility, rather than dealing with such a high volume of atypical and large pieces. So I've been pretty heavily digging into a lot of skills that I've learned as an architect in an environment that's not in a non-architectural environment. So I think I might end it here, but please ask some more questions about this. Again, it's really difficult for me to present on this, but I'm happy to answer any questions that might come up.
Great, thank you both so much. It's really interesting to see the paths you both have taken. I guess the first question that I have is, maybe you could just talk to the students about how you both became interested in robotics. Like, you both went to architecture school. Was it something was it a class you took there or a professor you had? And then maybe also your experience with coding or like using Grasshopper, was that something you had done by yourself or in school? And just your thoughts around starting, I guess, in fabrication.
Well, for me, I didn't, I was mostly looking at 3-axis machines in school. I did teach with Julia, and I found the experience of dealing with.
Yeah, you're mute. It's okay. Yeah, maybe Keith, you can go.
Sure. So has technical difficulties. So robotics, yeah, was really at UCLA. I was in Greg's studio with Julia, and we had a lot of time playing with the robots, kind of coming up with fun new ways to make them do interesting things. And that was really inspiring. I came into UCLA already kind of a seasoned fabricator of CNC and things like that, but really taking it to the next level, incorporating robotics. It's an interesting thing to try and scale up to manufacturing at a large scale. It's not quite as applicable at Arktura as I think I'd like it to be, We use it when we need to, and it's an interesting tool where it can solve a problem that when there's nothing else that can do it, the robot can do it. So that's an interesting application. Yeah, Grasshopper is really, and programming in general is really, I think the lifeblood of how we make digital manufacturing work, because it's really how you take something complex or develop something complex, but make it in a smart way where you can actually then build it. It's really easy to make a cool rendering, but I'm sure Erin can speak to the same thing. If you don't actually have usable surfaces and accurate models to then dice up and make parts from, you don't really have anything. So using software that can allow you to design in, the way you need to divide something up or slice something, or set relative sizes of things to each other so that you can work from it and not just make a pretty rendering, is really critical to anything that you're actually going to manufacture.
Yeah, I totally agree. I would like to bounce back a little bit on if nobody can do it, the robots can do it, because that gets thrown at me all day in the shop. And I have to argue that point that actually I cannot machine magic this into compliance. And maybe that's kind of where I can emphasize the difference between working in a strictly research environment as opposed to working in a production environment that's still extremely research heavy. We use tools like Rhino and Grasshopper very extensively. I know a lot of people get out of school and they kind of complain they don't get to use a lot of the fun toys they've spent a lot of, and skills they spent a lot of time learning. But in my experience, Grasshopper and Rhino are extremely important to our workflow. We're working with some extremely atypical and difficult parts that I really wouldn't be able to optimize the kinematics or get the robot to resolve itself around the parts if I didn't have basically a day to week ahead of time to kind of plug it in and work out some of our more complicated problems that we have. So, using Rhino and Grasshopper for things like, placement of the part in the cell, optimization, as well as just technically executing the piece is extremely important. And also kind of, as Keith was saying about kind of the objects that you're working from, I also find that using scripting and programming to deal with complex and heavy metadata is also incredibly important. I've been kind of crunching the master model from this project, which again has 1,500 unique parts. And if our subcontractor who does our frame mislabels one of the brackets, it can send my entire script crashing. So learning how to use Grasshopper cleanly and efficiently and effectively can really save hours of time. Like I'm looking at right now, basically optimizing the placement of each panel from the entire project and being able to see what are the implications of the size, placement, and positioning to our workflow, and what it means to us actually being able to complete the project on time. And it is immensely helpful to be able to do. We really couldn't, we really couldn't be successful if we didn't have these tools. It's so much more helpful than even programs like PowerMill, which are kind of like the heavier CNC programs. It actually has been immensely more helpful than that, because even though these are extremely robust programs in regards to machine control, it's really only so helpful if we can't have effective, planning and processing of data. So.
Awesome. So I guess going off of that question, one of the students from the JumpStart program had a question, I guess for both of you, about programs and technology. So you guys have talked a lot about, Grasshopper and CNC, and we've heard Yulia talk about 3D printing. Like, are there any other technologies or programs that you hope to be able to implement into your workflow that maybe right now are not so common? It's kind of a large question, but maybe if not. Oh, okay, yeah, Keith, sorry.
It's an interesting problem or question to answer, because our company is so, everything we do is based on sort of pushing the envelope technologically, and so we use 3D printing. I think the way that an architecture office used the plotter 10 years ago. It's just one of the ways that we output information now. It's not a novelty. It's not, even in, at offices I worked at in the past, it was a way to at least kind of visualize something you couldn't visualize in a different way. Now it's a direct part of our workflow, like making tooling and fixtures and components using a 3D printer is just the way. It's not a novelty or anything like that anymore. So at this point, I think we've found that there aren't a lot of new technologies that are kind of better than the ones that we have. And when we do run into a problem like that, we now call upon our programmers to write new software or write our own plugins or do things that, there's not necessarily a new piece of technology that we need to acquire. We might need to upgrade to a more capable version of a robot or something like that and add additional features. But really, those are incremental improvements. But right now, it's a really, really cool and interesting time to be doing kind of digitally driven fabrication because there's so many really accessible, you name a way to cut something using a computer-driven tool, we've got it because each one has their own application. And so it's an interesting time to be able to leverage all of those tools together to output unique products and unique solutions.
Yeah, I fully agree. I mean, we use 3D printing, robotics, and CNC cutting on a daily basis. I'd also like to just emphasize really what you can gain by getting facility with these tools and equipment, because one thing that we use pretty heavily in our plant are full-scale mock-ups and tests. And I couldn't recommend it more when you have a project is to work out the details in full scale, because things that you would never guess is tripping up your entire process can really only be found out by doing, full scale and very thorough research when it comes to, materiality and technology, things like turning radius, things like, the size of the piece, how you'd like to panelize it. Because I know a lot of problems that I'm kind of beating my head against right now are just, problems of panelization and robotic reach. And if you're able to really use these tools as kind of a master builder and gain full facility over them, you're able to have a degree of control over your projects as an architect that you otherwise wouldn't be able to. And, now in a production environment, the skills of an architect are now becoming the skills of the craftsperson. So you are not just producing paper documents anymore. You have the ability to produce a 3D model as a legal construction document. And if you're able to communicate with whoever's building your project for you effectively, then you have a remarkable amount of control in regards to the quality of your project, as well as the cost, which can make or break it being able to actually be produced. So I couldn't recommend getting your hands dirty and learning how to use these tools effectively and have them not only make your projects possible, but also drive your designs in a generative way.
Cool. And Keith, I saw you answered this question already, but I think it'd be good for everybody to hear your answer, and perhaps you can expand on it a bit more talking out loud. But could you talk about your offices, where you guys pull inspiration for the design from?
Sure, absolutely. So the question is, how do you come up with designs of systems and what kind of things have inspired the design? So our office, it's lots of different places. So we have our own in-house designers who design products, and we actually have our own product lines that we sell that are kind of already ready to go for different applications. And a lot of the patterning we design into those is inspired from nature or mathematical Voronoi and things like that very interesting cellular generation tools and things like that. And a lot of the designs, depending on maybe the sophistication or the budget or prestige of the project, the architects or the owners will come in with a lot of the design or the inspiration for the design already. That's a big part of what we do is taking a very loose concept sometimes and helping turn that in, apply our manufacturing know-how and turn that into something that can be built and will still achieve the aesthetic intentions of what the original designer was going for, but can be built and can be panelized and systemized and still make it through a doorway, and all of those things that you have to apply to a project to manifest it.
But I think what I would like to add, Keith, what you mentioned, you talk about products, and for some of our students, it might not be clear what you mean by products, because products in terms of architectural terms. So how can we take architecture and instead of designing houses, design components of houses or buildings, which then can be sold as a product to many different buildings, right? That's the kind of term what you defer to when you talk about products. So,
exactly,
right?
Yeah. So we make something as simple as a 2 foot by 4 foot ceiling tile, ceiling panel that if you look up in your classroom, there might be one in there. But we make one that is digitally bent, laser cut aluminum that has a pattern that when you assemble the panels together, they all tile together, and the pattern propagates across the ceiling. So we take.
Go ahead.
So we just take what may be kind of a conventional architectural product that you might use in a commercial building and apply contemporary design aesthetics and manufacturing techniques to make a newer, better, more interesting version of that. That's when I say products, that's the kind of things I'm talking about.
And do you mean you also compete with standardized products which are out on the market? So you're kind of offering something like a special edition or addition for that? So how are you competing price-wise?
I think we are very competitive, and I think one of the reasons that so to answer your question, yes, we're directly competing with kind of more conventional products on the market, and one of the reasons we are able to offer, in my opinion, much more interesting products for a competitive price is we leverage digital tools, we leverage our manufacturing know-how. We are able to design smarter systems that allow maybe faster and less expensive installation by Arktura doing more work in our factory before it ships out to the job site, or designing better connection details or ways of simplifying how something goes together. We can massively reduce the overall cost of installing the product, purchasing it, and maintaining it. So really leveraging those tools and design know-how is our advantage.
Very cool. A question for Erin. Can you describe more your collaboration with architects and facade consultants and how the division of labor ends up breaking down?
Oh man, that's a question. I mean, initially when I had arrived at Kreysler, we hadn't gotten the robots running yet. So I was kind of thrown at them to develop a production strategy. And a lot of that involved back and forth with the project architect to go and kind of analyze the finishes we were producing, decide what was within our range of acceptability, and make sure that that was also acceptable for the client and allowed us to work at an acceptable rate in which to keep the panels moving, because the robots are our most limited resource in the shop right now. So it's been an extremely push and pull relationship with both the architects, the client, and our internal quality control. So it's been an ongoing, it's definitely been an ongoing process and communication. There's definitely an ongoing and kind of back and forth communication style between all involved parties. And anytime we have a process change or shift anywhere upstream, being almost at the very end of production, it impacts our workflow as well. So we've had to continually adapt our processes, test our results, and log, what our RA values are for finish, and make sure that we're still meeting, visual and color standards. So it's a lot of communication between all all parties.
I guess maybe a follow-up to that is like, do you guys get at all like an input in the design? Like, do you go back to the architect and say like, hey, this isn't working, can we change it to be like this? Or are you just trying to really execute exactly what they're sending to you?
We have some degree of control over that. Basically, if like, one piece gets, cut incorrectly and it's really important, or if there's an engineering change, we can, but it's extremely difficult to do. So unfortunately, we can't. And it makes it really difficult for a lot of our very atypical parts. So unfortunately, we didn't have that back and forth early on in the process. But I think looking forward, if that's possible, it could definitely cut a lot of time and costs out for sure, because it's pretty. And again, kind of harkening back to scripting and Grasshopper, using these tools are how we basically analyze what we can do with our current equipment. We have very large robots. We're currently working on like a 70-foot track with 2 large Kamau arms. Our CNC gantry is larger than most houses in Los Angeles. So even though it seems like we have kind of this unlimited production capacity, anytime we get something that's 6 inches larger than our CNC gantry, it will delay us by several days on occasion, and then we'll have to compensate with other panels and plan accordingly. Same thing with robotics. It's extremely difficult to tell, at a glance what will fit in the cell, but we have to use tools like Grasshopper to basically pre-program everything to ensure it will fit and to ensure the best placement. So when we have rigging bring the parts into the robotic cell, we can give them pretty precise instructions. Like, I've been trying to narrow it down basically to 2 measurements that I give our rigging team, just based on how the brackets are structured and what legs we place them on, so we can move the part and position it in the cell while still keeping the instructions to the team to be as clear and concise as possible. So I don't know if that answer is helpful or not, but
Yep, I guess just good to know that it's always complicated. So yeah.
Yeah, mostly due to the scale of the project. The politics of changing anything are almost impossible, but it would.
So I guess unless any of the students have any more questions, I think we can wrap up 2 minutes early. Thank you both so much for coming and talking about what you have been working on since graduating. Julia, if you have any closing remarks.
Yeah, I just want to thank both Keith and Erin for joining us today, and all the students who dedicated their time to listen in today, and all the staff. Really appreciate that. And I think it was really inspiring for me to see Keith and Erin's work and the offices they work with today, seeing kind of where you took your education and what you learned at UCLA and how it's being applied professionally in the industry. It makes me really happy, Erin, to hear from you, and also from you, Keith, how much you implement computational design and digital fabrication techniques, which is often questioned by students. What am I going to use this for? Where can I apply this for? And I think it's not only a great design tool, but as you both mentioned, an optimization tool, and kind of working towards more optimized, even more sustainable processes. And I think that's really great to see where you took it both. So nice to catch up with you and see you again. And I hope we see each other in real life. And I think I can mention also, Erin, that Kreysler is right now looking to hire some people. So if anyone in the audience from our staff is interested, do reach out to me, and I can send you some information what Bill has shared with me. Well, thanks again, all of you, and hope to see you in person soon.
All right, thanks.
Bye. Bye.